Therefore, aldehydes and ketones undergo nucleophilic addition reactions. Let's again write the general structure of a ketone and a general representation of the nucleophilic addition reaction. That's when a nucleophile approaches an aldehyde or a ketone. It attacks carbon of the carbonyl group. And again, that carbon is electrophilic due to inductive withdrawal and resonance withdrawal, as we have seen before. So the nucleophile attacks this carbon, and the carbon-oxygen double bond is broken, releasing electrons to the oxygen atom. So this is the nucleophilic addition product, where the nucleophile attacks again that carbon of the carbonyl group. This nucleophilic addition reaction can also be described as 1,2 addition. If we give this atom carbon of the carbonyl group number 1 and oxygen is number 2, so therefore this nucleophilic addition reaction is also described as 1,2 addition, because the nucleophilic addition reaction takes place over these two atoms, or the double bond, or which is formed by the two atoms, by carbon and oxygen. So this is a 1,2 addition reaction. It's a nucleophilic addition reaction, obviously. What if there is a double bond on the aldehyde or the ketone or the carbonyl compound in general, something like this? So there is a double bond between carbon number 2 and carbon number 3. This carbon, the carbon number 2, is described as alpha, so that's the alpha carbon. This carbon is described as beta, so therefore this compound is an alpha beta unsaturated carbonyl compound. What's unique about these carbonyl compounds, the alpha beta unsaturated carbonyl compounds, is that not only they are electrophilic at this carbon of the carbonyl group, but as a matter of fact they are also electrophilic at the beta carbon. So what's the evidence of that? Well, we can actually draw a resonance form for this alpha beta unsaturated carbonyl compound by doing something like that. So we can break the carbon-carbon double bond to make another double bond here, and as a result this carbon-oxygen double bond is broken. So if we do that, we can get another resonance form. And we could see clearly in this resonance form that the beta carbon has or bears a positive charge. So this is again, that's the alpha carbon, that's the beta carbon. The beta carbon bears a positive charge, and this is a clear evidence that that beta carbon is actually electrophilic. So this carbon is electrophilic. Of course, in addition to the original electrophilicity of that carbon of the carbonyl group. So therefore, alpha beta unsaturated carbonyl compounds, not only they are electrophilic at carbon of the carbonyl group, but also they are electrophilic at the beta carbon, as manifested by this electronic movement by resonance. So therefore, alpha beta unsaturated carbonyl compounds can potentially be attacked by nucleophiles at this carbon of the carbonyl group, and or the beta carbon, depending on the nucleophile. Let's now take examples of that, of the two types of nucleophilic addition reactions. Let's draw the structure of an alpha beta unsaturated carbonyl compound again. So something like that. So a carbonyl compound that has a double bond between the alpha carbon and the beta carbon. And as we have seen before, these alpha beta unsaturated carbonyl compounds are electrophilic not only at carbon of the carbonyl group, but also at the beta carbon. So some nucleophiles can actually attack this carbon of the carbonyl group, and other nucleophiles can attack the beta carbon of this alpha beta unsaturated carbonyl compound. And again, we have seen before that beta carbon is actually electrophilic as we have seen before, or evidenced by resonance. Some nucleophiles attack this carbon, or carbon number 1 if you like, and if they do, that nucleophilic addition reaction or that nucleophilic attack is described as 1,2 addition, because the addition is on atom number 1, which is carbon of the carbonyl group, and atom number 2, which is oxygen of the carbon oxygen double bond. So if a nucleophile therefore attacks this carbon number 1 if you like, of the carbon oxygen double bond, so something like that, a typical or a classical nucleophilic addition reaction, this nucleophilic addition reaction is also described as 1,2. So let's write the product first. So this is the 1,2 addition product. So this addition, or this nucleophilic addition, is described as 1,2 addition if the nucleophile attacks carbon of the carbonyl group. What if a nucleophile attacks the beta carbon, and of course the beta carbon again is electrophilic? Now the addition is not 1,2 addition, or is not described as 1,2 addition. Let's show that, and then we can take it from there on for a better description of that different type of addition reaction. So this is again the alpha beta unsaturated carbonyl compound. If a nucleophile approaches a certain nucleophile, of course, with certain characteristics, as we will see shortly, if a nucleophile attacks that beta carbon, so we can show this with curly arrows. So the nucleophile attacks the beta carbon. This carbon-carbon double bond is broken. A carbon-carbon double bond is subsequently formed, and this carbon-oxygen double bond is broken. Now, if you look at this reaction, or this type of nucleophilic addition reaction, it's clear to us, okay, that the nucleophile actually takes place over this conjugate system, if you like, or this conjugate unit, a double bond, a single bond, and a double bond. So this is a conjugate unit, just like a simple butadiene, if you like. But of course, obviously, the difference here is you have an electronegative atom. So this is a conjugate unit. The nucleophile attacks the beta carbon of this conjugate system. So therefore, this type of addition is called conjugate addition. Let's write the product, and then we can write these descriptions again. So this is the product, or the intermediate at least, of this nucleophilic addition reaction. And remember, that's the alpha carbon, that's the beta carbon, obviously that's the alpha carbon and the beta carbon, and the new bond is between the nucleophile and the beta carbon, basically the nucleophilic center, or the nucleophilic site in the nucleophile, and the electrophilic site in the alpha beta unsaturated carbonyl compound, or the beta carbon. Now, this type of nucleophilic addition is described as conjugate addition, because it has taken place, or it does take place, over a conjugate system or a conjugate unit. Now, if we give this conjugate unit, or conjugate moiety, if you like, numbers, as we have done before on the carbon-oxygen double bond, we would give the beta carbon number 1, the alpha carbon number 2, this carbon number 3, and that oxygen number 4. So we can say that the nucleophile, or the nucleophilic addition, has taken place over this conjugate system, beginning with atom number 1. So all atoms number 1, or carbon number 1, carbon number 2, carbon number 3, and oxygen number 2, all of them participate in this conjugate addition. It is actually correct to also describe this conjugate addition as 1,4. 1,4, so the nucleophile takes place over 1, 2, 3, 4 atoms, or this conjugate system. So therefore, another description of this nucleophilic addition reaction is actually 1,4. So 1,4 addition if a nucleophile attacks the beta carbon of an alpha beta unsaturated carbonyl compound. So in summary of this, if a nucleophile attacks carbon number 1, or carbon of the carbon-oxygen double bond, the nucleophilic addition is described as 1,2 addition, whereas if a nucleophile attacks the beta carbon of an alpha beta unsaturated carbonyl compound, the nucleophilic addition is described as conjugate addition or 1,4 addition. Let's now take examples of the two types of nucleophilic addition reactions. So this is the, let's draw the structure again of an alpha beta unsaturated carbonyl compound. So something like that is correct. So it's actually an alpha beta unsaturated carbonyl compound, or alpha beta unsaturated ketone, specifically if R is an alkyl group. Now, certain nucleophiles do 1,2 addition and other nucleophiles do 1,4 addition. In general, strong nucleophiles or hard nucleophiles such as organolithiums or organomagnesium reagents or Grignard reagents favor 1,2 addition. So something like this, if you react this alpha beta unsaturated carbonyl compound with an organolithium whose general structure is of that type, then the organolithium favors a 1,2 addition. That's because the organolithium is a very strong nucleophile. It's a very strong base, and of course that's due to the high electropositivity of lithium. Remember, lithium is located in group 1A, so the most electropositive, if you like, atom, lithium. So the nucleophilic addition product will be a 1,2 addition product. Okay, so this is an example, therefore, of a 1,2 addition or a nucleophilic addition of 1,2 type. That's when the nucleophile is hard or strong, a strong nucleophile or a strong base. We can add to that category or Grignard reagents, because again R or a carbanion, if you like, or the nucleophilic carbon in Grignards is bonded to magnesium, and again magnesium is located in group 2A alkaline earth metals, and they are very electropositive metals because they are at the far left of the periodic table. Remember, electropositivity decreases from left to right in the periodic table. So organolithium reagents or Grignards, we can also add Grignards to them, or even hydrides, okay, such as sodium borohydride, for example, or lithium aluminum hydride, hydride ion being a strong base. All of these nucleophiles favor most of the time, okay, 1,2 addition type. Now, other nucleophiles which are not as hard, if you like, or as strong, such as, well, the moderate nucleophiles, and here we talk specifically or very neatly actually about organocopper reagents or Gilman type reagents where R is bonded to a copper, and of course copper is not as electropositive as lithium or magnesium as in the organolithium reagents or organomagnesium reagents or Grignards respectively. That's because copper is not as electropositive. Copper is a transition metal. It's actually at the end of the first row of the transition metal block. So it's much less electropositivity than lithium or magnesium. So therefore, if you react this alpha beta unsaturated carbonyl compound with a Gilman type copper reagent or organocuprate, the cuprate will attack the beta carbon of the alpha beta unsaturated carbonyl compound, thus favoring a 1,4 addition type or conjugate addition. So the product would therefore be something like this, where R prime coming from the cuprate now is bonded to the beta carbon of the alpha beta unsaturated carbonyl compound. It's clearly in the end, of course after addition of H3O plus or a mild acid, because remember the product at the end of this conjugate addition is an enolate, obviously, but the enolate, if it's treated with a mild acid, it gets protonated to an enol, or it gets converted in the end to the ketone. The enol, even if it's small, it will tautomerize, obviously, to the ketone. The final product is a product where the new group coming from the cuprate gets bonded to the beta carbon, and as a result of this 1,4 addition type reaction or conjugate addition.